Picture this. You wake up on a freezing, bitter winter morning.
Ugh, the worst.
Right. You've got your coffee in hand, you're shivering a little bit before the house is fully warmed up, and you look out the window to check the weather.
Yeah, just trying to see how much snow fell.
Exactly. But instead of just taking in a nice frosty lawn, your eyes lock onto your outdoor heat pump, and, your stomach just completely drops.
Because it looks terrible out there.
Yes. Because that heavy metal box sitting out there in the yard is either completely encased in a thick white coat of frost, or, even worse, it's billowing massive clouds of steam like something inside the chassis just caught on fire.
Yeah, it's a deeply visceral reaction. You see smoke or you see ice where there absolutely shouldn't be ice, and the immediate homeowner instinct is, well, the machine is actively destroying itself.
While you watch helplessly from the kitchen window, right?
Exactly. You're just watching it happen.
That instant panic is so real. But welcome to today's deep dive, because our mission right now is to take that exact panic away from you. We're going to decode the exact physical mechanics of what is happening inside that machine on a freezing winter morning.
Which is so important to understand.
It really is. And to do this, we are working from a fantastic, comprehensive guide featuring Dave Hartzell. Now, Dave is the owner of Hartzell's Heat and Air in Kingfisher, Oklahoma.
A true expert in the field.
Totally. And let's get the credentials right up front, because, they established the baseline for everything we're about to discuss today. Dave is a NATE-certified master HVAC technician who has exactly 47 years in the trade.
Wow. 47 years.
Yeah, 47 years of diagnosing every conceivable thing a heating system can possibly do.
And that NATE certification is a really important detail to single out here. NATE stands for North American Technician Excellence. It is like the absolute gold standard in the heating and cooling industry.
It's not just a basic piece of paper.
Oh, not at all. It means Dave hasn't just spent 47 years turning wrenches. He has passed rigorous, specialized testing that proves a deep, comprehensive mastery of thermodynamics, electrical systems, and, airflow dynamics.
So he really knows his stuff.
He really does. That verified expertise is exactly why we can trust the absolute baseline rule that Dave sets for this deep dive.
Which is that frost and steam do not automatically equal a broken system.
Precisely. There is a perfectly normal, healthy version of this frosty steaming machine, and there is a severely broken version.
And our goal today is to equip you, the listener, with the knowledge to easily and confidently tell them apart without having to crack open a massive technical manual.
Nobody wants to read those anyway.
Definitely not before coffee. Okay, let's unpack this, because before we can even begin to diagnose why ice is forming on the outside of the box, we have to talk about the core physics of how this machine is heating your house in the first place.
Yeah, this is where people really get tripped up.
Right, because when it's 20 degrees outside and your breath is fogging up the air, how can a machine possibly pull warmth out of a freezing environment? Like, Dave uses this analogy in his guide of a cold drink sweating on a humid summer day.
It's a great analogy, actually.
Is it? Because applying a sweaty glass of iced tea to a heavy metal box in the dead of winter feels like a pretty huge stretch to me.
I get that. It requires a fundamental shift in how we perceive temperature, really. We are so used to traditional gas furnaces.
Right, where you burn something to get hot air.
Exactly. A furnace creates heat through combustion.
Yeah.
You ignite a gas flame, you blow air over a hot metal heat exchanger.
Yeah.
But a heat pump doesn't burn anything.
Nothing at all.
Nothing at all. It doesn't create heat out of thin air. Instead, it's a transporter. It moves thermal energy from one place to another.
But I'm trying to visualize this. If I step outside and it's 20 degrees, I am instantly losing body heat. The air feels like it has literally zero heat to offer. Where is the thermal energy coming from?
Well, this is the part that feels like magic, but it's just pure physics. Even in freezing air, there is still an abundance of heat energy.
Wait, really? In 20-degree air?
Oh, absolutely.
Right.
In physics, heat is just molecular movement. The only time there is zero heat energy in the air is at absolute zero.
Which is, what, super cold?
It's negative 459 degrees Fahrenheit. So since it's only 20 degrees outside your house, there's actually a massive amount of thermal energy bouncing around in the atmosphere.
Okay, that makes sense.
The trick is just capturing it. And to grab that scattered ambient heat, the heat pump's outdoor coil has to intentionally get colder than the surrounding outdoor air.
Oh, I see. It's like water flowing downhill. Heat always moves toward cold. So if the air is 20 degrees, the only way to get heat out of it is to make the machine itself even colder, like 0 degrees.
You hit the nail on the head. Inside that outdoor unit is a compressor and a network of copper coils filled with a specialized chemical called refrigerant. And the compressor basically manipulates the pressure of that refrigerant. By dropping the pressure drastically inside that outdoor coil, the temperature of the refrigerant plummets well below freezing.
So the coil gets super cold.
Right. So now you have a coil sitting at, say, 0 degrees and a fan pulling 20-degree outdoor air across it. Because the air is warmer than the coil, the thermal energy in the air transfers into the refrigerant.
And then it brings it inside.
Yep. The system pumps that absorbed heat inside your house, compresses it to make it even hotter, and blows it right into your living room.
That makes perfect sense. I always think of it like a bicycle pump. Like, if you've ever manually pumped up a bike tire, you know the barrel of the pump gets really hot.
Oh, yeah, definitely.
Compressing a gas creates heat, and if you let the air out of the tire quickly, the valve gets ice cold. Expanding a gas drops the temperature. The heat pump is basically just doing that on an industrial scale.
That is a brilliant way to picture it. But here is the catch, and this brings us back to Dave's iced tea analogy.
Ah, right, the iced tea.
Yeah, because that outdoor metal coil is sitting there running at 0 degrees to absorb heat, it is interacting with the natural moisture in the winter air.
Just like the summer humidity on the glass.
Exactly. Just like a cold glass of iced tea on a summer day pulls humidity out of the air and causes condensation to beat up on the glass.
Except, in the winter scenario, the metal coil is well below 32 degrees, so it's not going to sweat liquid water.
It instantly freezes. The moisture in the damp winter air doesn't just beat up, it turns immediately into frost on the incredibly thin metal fins of the coil.
Wow.
And the colder and damper the ambient weather is, the faster that frost builds up. So when you look out your window and see a light, uniform coat of white frost covering the sides of your heat pump, it is absolutely not a defect.
It's actually a good thing.
It's actual visual proof that the machine is successfully dropping its internal pressure, getting colder than the outside air, and pulling heat into your home. It's doing exactly what it was engineered to do.
It's almost like a badge of honor. It's out there working hard. But that leads to an incredibly obvious problem.
What's that?
Well, if the machine is constantly freezing moisture out of the air, minute after minute, hour after hour, why doesn't it just accumulate ice until it turns into a permanent solid glacier sitting in the middle of your yard?
What's fascinating here is the sheer ingenuity of the system's self-preservation mechanism.
Okay.
The engineers who designed these systems fully understood that pulling heat out of freezing air meant ice accumulation was completely unavoidable. So they gave the heat pump an automatic, built-in defrost cycle.
How does that work?
Well, every 30 to 90 minutes, depending on the conditions, a sensor on the outdoor coil realizes the frost is getting too thick and restricting the airflow. At that moment, the machine essentially decides it needs to take a breath, and it physically flips its entire operation into reverse.
Into reverse. Wait, are we saying the machine stops heating and starts running as an air conditioner in the middle of winter?
For a span of about 5 to 15 minutes.
That is wild.
I know, right? There's a mechanical component inside the system called a reversing valve. When the control board triggers a defrost, this valve shifts. It takes the hot, high-pressure refrigerant gas that was heading inside to warm your house and temporarily redirects it back outside into that frozen outdoor coil.
To melt the ice.
Exactly. It takes the heat it was gathering and uses it to violently and rapidly melt all that accumulated frost.
Here's where it gets really interesting, because what that defrost cycle looks and sounds like to the homeowner standing at the window is absolutely terrifying if you don't understand the sequence of events.
Oh, it causes so much panic.
Let's break down the sensory details so you, the listener, know exactly what this normal cycle feels like. First, there's the visual of the steam. Dave points out that the frost melts so incredibly fast from that sudden surge of superheated refrigerant that it creates a massive amount of rising vapor.
And when that hot vapor hits the freezing cold ambient air outside, it immediately condenses into a thick, billowing cloud.
It looks like smoke.
It looks exactly like heavy smoke pouring out of the top of the unit. Homeowners see this and naturally assume the fan motor is burning up or an electrical fire has started.
Which is a fair assumption.
It is. But nothing is burning. You are literally just watching warm meltwater flash evaporating in freezing air.
It's completely dramatic, and it's not just a visual shock. It's auditory, too. You are going to hear a massive sound shift from the machine. Dave describes a loud whoosh sound.
Yeah, that whoosh is the sound of high-pressure gas suddenly changing direction.
Like letting air out of a balloon all at once?
Kinda, yeah. When that internal reversing valve shifts its internal slider to reroute the refrigerant, the pressure equalization makes a very distinct almost startling rushing noise.
And the fan stops, right?
Yes, the fan on the outdoor unit will also completely stop spinning during this time. The whole acoustic character of the machine changes from a steady hum to total silence accompanied by a hissing whoosh.
And there is a tactile element inside the house, too, which I think is the part that drives the most service calls.
Oh, absolutely.
Because the system is temporarily running in reverse,
Sure.
stealing heat from the house to melt the outdoor ice, the air coming out of your indoor vents will suddenly feel noticeably cooler.
It is entirely counterintuitive. I mean, you are relying on this machine for warmth during a freeze, and suddenly it blasts you with cool air while puffing smoke outside.
It feels like a betrayal.
It really does. Now, most modern systems will simultaneously activate electric backup heat strips inside your ductwork to temper that cold air and keep you somewhat comfortable, but you might still notice a temperature dip.
I completely see why people panic. You see smoke outside, you hear a loud clanking whoosh, the fan stops, and suddenly cold air is blowing out of your vents.
Wow.
Your immediate thought is going to be that the system has suffered a catastrophic failure.
But understanding this cycle changes your entire relationship with your home's mechanical systems. It's not failing. It's performing a vital, healthy function. It melts the ice, the water drains away, the reversing valve flips back over with another whoosh, the outdoor fan kicks back on, and it goes right back to pumping warm air into your living room like nothing ever happened.
Okay, we have firmly established the baseline. A frosty, steaming, whooshing heat pump that blows cool air for 5 minutes is a highly intelligent machine taking care of itself.
Correct.
But we have to transition to the dark side of the winter morning scenario. When should you actually hit the panic button? How do we definitively know when the normal, healthy frost crosses the line into the broken version?
Well, the phrase Dave uses in his guide is when the ice wins.
When the ice wins. I like that.
Yeah, and there are very distinct visual warning signs that the machine is losing the battle against the elements. The most obvious indicator is the physical nature of the ice itself.
Okay.
We are no longer talking about a light, white, snowy layer of frost that you could easily brush away. We are talking about a thick, solid, dense block of hard ice, completely encasing the entire outdoor coil.
Like an iceberg.
Think of a literal block of ice you'd pull out of a deep freezer.
And where that ice is located is a massive clue, right? Because normal frost cloops the sides, right on those thin metal fins.
Exactly. But if you see thick ice building up on the very top of the metal cabinet or creeping its way inside the grill and forming over the fan blades, that is a huge red flag.
Ice in the fan is bad.
Ice should never reach the fan blades. And time is also a critical factor. If you see that solid block of ice sitting there for an entire day and the machine never seems to produce that cloud of steam to melt it off, well, the defrost cycle is failing.
Dave also mentions looking closely at the concrete pad or the base of the unit, right?
Yes, sometimes the defrost cycle is trying to work, but the water has nowhere to go.
Why wouldn't it have anywhere to go?
If the drain holes at the bottom of the unit are clogged with debris, the melted frost just pools in the base pan. When the cycle ends, that puddle refreezes into a solid sheet of ice. Yeah, and over days or weeks, that ice sheet grows thicker and thicker from the bottom up until it actually swallows the lower portion of the coil.
That sounds awful.
And of course, the ultimate undeniable sign that the ice has won the battle. The ambient temperature inside your house simply isn't recovering. The thermostat is set to 70, but the room is sitting at 62 and dropping, despite the system running constantly.
So if I'm looking out the window at a solid glacier of ice that has consumed the fan blades, and I'm shivering in my kitchen, what actually causes the physical system to fail this severely?
That's the big question.
Because the immediate assumption people make, like the analogy everyone defaults to, is that it's just out of fuel. Kind of like a car sputtering out of gas. Does a frozen heat pump just mean it used up all its refrigerant?
This raises a profoundly important question, and it gives us a chance to correct one of the most common misconceptions in residential heating.
Okay, lay it on me.
A heat pump does not consume refrigerant. It doesn't burn it up like a car burns gasoline.
It doesn't.
Nope. The refrigerant runs in a completely sealed, pressurized, closed copper loop. It just circulates round and round endlessly. If your system is low on refrigerant, it means there is a physical leak somewhere in the copper lines or the coils.
Oh, so it didn't use it up.
Right, it lost it to the atmosphere.
But I'm trying to connect the dots here. Why does having less refrigerant make the machine freeze over into a solid block? Shouldn't less refrigerant just mean it does less heating, not that it turns into an iceberg?
It comes back to the relationship between pressure and temperature that we talked about earlier.
Right, the bike pump analogy.
Exactly. According to the laws of thermodynamics, if you have less refrigerant flowing through the same fixed volume of copper tubing, the overall pressure inside that system drops significantly.
And low pressure means low temperature.
Yes. When the pressure drops, the temperature of the refrigerant drops with it. So instead of the outdoor coil running at 0 degrees, a low refrigerant system might have a coil running at, say, -20 degrees.
Wow, that's way colder.
It gets drastically colder than the engineers ever intended. This causes moisture to freeze onto the coil so incredibly fast and so thick that the normal 15-minute defrost cycle simply doesn't have enough time or heat to melt it all off.
It just can't keep up.
Right, the ice compounds cycle after cycle until it's a solid brick.
That makes perfect sense. The pressure drops, the temperature plummets past the design specs, and it triggers a runaway freezing event. But Dave notes it isn't always a leak, right?
Right. Think back to that reversing valve we discussed.
The one that flips it into AC mode.
Yeah, the physical brass valve that shifts to reroute the hot gas and melt the ice. That valve operates using a small electrical solenoid.
Okay.
If that solenoid burns out, or if the internal slider mechanically jams, the unit literally cannot switch directions. The compressor keeps pumping, the frost keeps building, but the heat pump can never trigger the defrost cycle, no matter how much ice builds up.
Or it could be a communication failure, like the brain of the machine failing to send the signal.
Exactly. There is an electronic control board and specific temperature sensors strapped to the outdoor coil. Their entire job is to monitor the frost thickness and tell that reversing valve when to shift.
So if a sensor breaks,
If a sensor fails or a wire shorts out, the control board never receives the data that the coil is frozen. The machine basically operates blindly, assuming everything is fine, while the ice slowly suffocates it.
that's tragic.
And Dave also emphasizes the role of choked airflow. If the outdoor fan motor seizes up and dies, no air moves across the coils, the heat transfer stops entirely and the coil freezes solid.
The overarching theme for all of these root causes, a pressure drop from a leak, a physically jammed reversing valve, a failed sensor, a dead fan motor, is that diagnosing them is strictly tech territory.
Oh, completely.
These systems deal with high-voltage electricity and pressurized chemicals. Finding a microscopic leak or testing electrical resistance on a circuit board requires highly trained hands, specialized gauges, and a deep working knowledge of thermodynamics.
You really don't want to mess around inside there.
So what does this all mean for you, the homeowner listening right now? If diagnosing a pressure drop or a stuck solenoid is strictly off limits, what is your role?
That's what everyone wants to know.
Because human nature is incredibly predictable. When we see something physically wrong, our instinct is to step in and forcefully fix the immediate visual problem. What can you safely do to help your system survive the winter?
Well, the homeowner's safe zone is entirely focused on the perimeter.
The perimeter.
Yes. The safest and most impactful action plan is all about ensuring the machine has the physical room to breathe. That machine needs to pull massive volumes of air across its coils to extract heat.
Right.
So if there was a heavy snowstorm overnight, bundle up, go out there, and gently brush the accumulated snow off the top and sides of the unit. You can use a soft broom or just your gloved hands.
But we want to be clear, we are not talking about excavating it. We are just clearing the immediate obstructions.
Right. Look around the base, clear away any wet, heavy leaves, dead tall grass, or random debris that might have blown against the coil vents.
What about snowdrifts?
If a massive snowdrift is building up against one side of the house and burying the unit, carefully shovel that drift away so the unit has clear airspace on all sides. If the air can't physically reach the coils, the thermodynamic process breaks down entirely.
And Dave points out there is a crucial indoor component to this safe zone as well, which most people never connect to an outdoor ice problem.
The indoor air filter.
Yes.
It sounds almost too basic to mention, but maintaining a clean indoor filter is absolutely critical to the survival of the outdoor unit.
Why is that?
Because these systems are intimately connected in a closed loop. If your indoor air filter is heavily clogged with dust, pet hair, and debris, it severely restricts the volume of air blowing across the indoor coil.
And that messes up the whole process.
Exactly. That lack of indoor airflow disrupts the heat exchange process inside, which wildly alters the temperature and pressure of the refrigerant returning to the outdoor unit.
Oh.
A dirty indoor filter forces the outdoor compressor to work harder, run hotter, and struggle significantly more with frost accumulation. Maintaining pristine indoor airflow directly supports the health of the outdoor defrost cycle.
Okay, clearing the perimeter and changing the indoor filter makes perfect logical sense. You are just helping the machine breathe. But now we need to address the human instinct to forcefully fix things.
Oh.
Let's cover what you absolutely, unequivocally must avoid doing when you find your unit frozen. Because when people see their vital home infrastructure encased in a solid block of ice, panic takes over, and they do wild things to try and manually help the defrost process.
People do the craziest things.
Do not, under any circumstances, take an ice pick, a screwdriver, a hammer, or a snow shovel and try to physically chip or smash the ice off the sides of the unit.
This is a warning that cannot be stressed enough. Those metal fins on the outside of the coil are incredibly thin, delicate aluminum.
Like paper thin.
Yes. And sitting right behind those paper-thin fins are the copper tubes carrying the highly pressurized refrigerant. If you slip with a scraper or jab a screwdriver just a fraction of an inch too deep, you will instantly puncture that copper tubing.
And that turns a bad morning into a nightmare.
You will hear a loud hiss as you vent your system's entire refrigerant charge directly into the atmosphere.
Oh, man.
You have just turned a simple, easily diagnosed sensor issue into a catastrophic system failure that requires replacing massive components. So put the tools down.
With the ice pick down, the other instinct people have is to treat it like a frozen windshield. Do not boil a pot of hot water on your stove and pour it over the machine to melt the ice.
Please don't do that.
You are dealing with high-voltage electrical contactors, sensitive electronic circuit boards, and electric fan motors. Dumping gallons of water into a freezing electrical cabinet is a guaranteed recipe for shorting out the entire system.
Absolutely.
And finally, do not try to unscrew the metal access panels to see what's going on near the compressor.
That is the ultimate line in the sand for a homeowner. If you have gently brushed away the surface snow, cleared the perimeter of leaves and drifts so the unit can breathe, and verified that your indoor air filter is clean.
Wait, no ellipses.
Right. I mean, if you've checked all of that and the unit still rapidly ices right back up into a solid block, or the ice stubbornly refuses to melt after a full day, or you see ice forming over the fan blades.
Or the house is just freezing cold.
Right. Or the temperature in your living room just continues to drop. That is your clear, undeniable signal to stop fighting the machine. You have successfully done your part. Now it is time to call for professional intervention.
Let's bring this all together. What we've learned today completely flips the script on that terrifying winter morning scenario. A uniform layer of white frost on the sides of your heat pump, a massive cloud of dramatic steam, a loud, rushing, whooshing sound, and a few temporary minutes of cooler air blowing from your indoor vents. These are not signs of impending doom.
Not at all.
They are the sights, sounds, and physical sensations of a highly intelligent piece of engineering taking care of itself by running a perfectly normal defrost cycle. But a solid, immovable block of hard ice climbing up into the fan cavity, or a house that just stubbornly refuses to get warm, that means the ice has officially won and the machine is crying out for professional help.
You know, if we connect all of this technical diagnostic information back to the broader picture, I really want to leave you with a final thought to ponder long after you finish listening.
What's that?
Consider the incredible, almost magical science of ambient energy.
Oh, yeah.
Even on a bitter, freezing winter day when the wind is howling and the frost is thick on the windows, there is still invisible thermal energy hidden in the freezing air all around us.
Just waiting there.
Exactly. It is just waiting for the right technology to capture it, compress it, and use it to keep our homes warm. It's a daily miracle of physics, thermodynamics, and engineering happening right outside in your backyard.
It really is a marvel when you understand the mechanics behind it. And if that daily miracle of physics in your backyard is currently frozen solid, encased in a block of ice, and failing to keep you warm, here is Dave Hartzell's specific message for you: do not keep fighting it.
Call the pros.
Remember, Hartzell's Heat and Air is a family-run operation. They hold the rigorous NATE certification we discussed, and they maintain a stellar 4.8-star rating across over 300 Google reviews.
And they know what they're doing.
Most importantly, Dave has been diagnosing these exact systems for exactly 47 years. You can find them in person at 602 South Main in Kingfisher, or you can book an appointment online anytime at hartzellsheetair.com.
Highly recommend them.
If your heat pump is losing the battle with the ice, call Hartzell's Heat and Air at 405-375-4822.
So the next time you wake up on a freezing morning, clutch your coffee to stay warm, and look at the kitchen window at that steaming metal box in the yard, you no longer have to panic.
You really don't.
You know exactly what the pressure, the temperature, and the valves are doing inside.
Thanks for joining us for this deep dive into the fascinating winter mechanics of heat pumps. Stay warm out there.